The Chatelier's principle. The Chatelier's principle pretty much tells you that when you have an equation, a reaction that is at equilibrium, if you do anything to this reaction such that you disturb the equilibrium, the reaction will act in such a way as to regain equilibrium. That's what the Chatelier's principle is all about. So when a disturbance is felt, the system will change to regain equilibrium. So if you feel a disturbance in the force, as Obi-Wan Kenobi will tell you, you gotta regain equilibrium, which I believe that was part of what he told Luke as well, right? If you disturbed, the equilibrium, you gotta regain equilibrium. And the disturbances, by the way, can be attributed to either removal or addition of reactants or products. So you could remove some reactants after you have attained equilibrium, and that will basically be a disturbance. You could add more reactants, that will be a disturbance. The same thing for products. But you could also change the volume and pressure of gases, and this will apply mostly if you just have gases in your equation, or even temperature. Temperature can also have an effect, as you'll see in the discussion. So let's start with the removal and see what happens with it. All right, so we're going to concentrate on this equation. H2 plus I2 yields 2HIs. The equilibrium expression is given right here, Hi to the second power, because the balancing coefficient, divided by H2 divided by I2. If you remove reagents, what ends up happening is that you now have less H2 and I2 than you would have want to have an equilibrium. And the moment you change the amount of reactants, this is no longer the equilibrium expression, this is the product constant, QC. And so what you do is you compare K and Q to each other. Specifically, you see the fact that, okay, you decrease the amount of reactants. Since the reactants are in the denominator, making the number smaller for the reactants will actually make the entire value of QC larger than the value of KC. And the idea is this. If you set this up alphabetically, so K before Q, if K is greater than Q, this is product favor, meaning that you're going to be shifting to the product side. And you can kind of see that with the inequality sign right here. Same thing for when Q is less than, then K is less than Q. The inequality symbol will be pointing to the left, meaning that this will be shifting to the reactant side. So if you set this up alphabetically and just compare the values of Q and K, or at least the proportions of Q and K to each other, you can tell whether this will be shifting to the product side or not. All right, in the case where Q ends up being larger because you made the reactant concentration smaller, while Q is larger than K, so that means that you're going to be moving to the reactant side. You'll be shifting to the reactant side. And another way to put it is that you remove reactants, so the equilibrium shifts to the side where you need to have now more reactants. Now, if you remove products, in this case, you'll have less products than you did have before. And because the products are on the numerator of the fraction, decreasing the amount of products decreases the value of K, meaning that Q is going to be smaller than K. And because Q will be smaller than K, this will be shifting to the product side. And yet again, removing a product shifts the equilibrium to the product side. Removing a reactant moves the equilibrium to the reactant side. So in essence, wherever you remove something, that's where the equilibrium is going to shift. Now let's take a look at what happens when you add things. In the case of adding reactants, what that means is that you're going to have a lot more reactants than what you had before. And that makes the denominator larger than in the equilibrium expression. So if the denominator becomes larger, automatically the value of Q is going to be less than the value of K. And if Q is less than K, then this will be moving to the product side. So in essence, what this is telling you is that you're adding more reactants, you're going to be shifting to the product side. So you can favor formation of products by adding more reactants. The same logic applies when you add products. If you add products, now your numerator is going to be larger than what you had before. And so the value of Q is going to be larger than the value of K. And so Q being larger than K means that you're going to be reactant favor. You'll be shifting to the reactant side. And another way to kind of describe this is that wherever you add things, you're going to shift the equilibrium to the opposite side of the reaction. This is kind of the opposite of removal. Wherever you remove things, that's where the equilibrium shifts. Wherever you add things, you shift the equilibrium to the opposite side of the equation. All right, now for volume, this is actually very much in tandem with gases. But the idea is this. Okay, so let's look at this equation. CH4 plus O2 gas plus CO, produces CO2 gas plus water. Now the water is a liquid, so that's not really gonna play a role in the equilibrium expression. So we just focus on the gases. CO2 gas to the first power divided by CH4 to the first power times O2 to the second power based on the balancing coefficients. All right, so this idea of changing the volume is only going to apply if you have gases. Okay, so let's take a look at what happens when we reduce the volume. In order to really tell what happens with the volume, consider the following. The concentrations shown in here are molarity concentrations. And molarity concentrations imply that you have moles divided by liters, and liter is the volume. So if you rewrite the concentration of CO2 as moles of CO2 over volume, and you keep in mind that the volume of all the gases is going to be the same because they're all going to be in the same container, what ends up happening is that when you rewrite this, you have moles over volume for CO2, moles over volume for CH4, but for O2, which is being squared, you'll have moles squared over volume squared. So the volume of the CH4 and the volume of O2 will combine to give you volume cube. And what that means is that you will only partially cancel out the volumes. One volume will cancel out partially with the volume cube. You're going to end up overall with volume squared on the denominator. And so now look at this. If you reduce the volume, this value right here in the denominator is going to become smaller. That will make the denominator fraction larger in general than what you have in the numerator. And because the denominator overall is becoming larger, the value of Q has to become smaller than the value of K. So this will be a product favor reaction. And if you want to look at it this way, reducing the volume ultimately shifted the equilibrium to the side that had the least amount of gases because you now have less room. So if you look carefully, here you have 1 mole of gas plus 2 additional moles of gases. So you have 3 moles of gas on the reactant side. On the product side, you only have 1 mole of gas. So reducing the volume will tend to shift the equilibrium to the side that has the least amount of gases, which in this case is the product side. And that's what we're seeing from the analysis shown right here. Now, increasing the volume for this same equation is going to have the opposite effect. The equation is still the same, concentration is still moles per liter, mole squared over liter squared. So you're going to have, once again, the volumes partly canceling out. You're going to end up with volume squared on the denominator yet again. But this time around, if you do increase the volume, the bottom fraction, so the red fraction right here, is going to become smaller. And if the bottom fraction becomes smaller, the value of Q is going to turn larger than the value of K. And when that happens, you have to shift to the reactant side. And so, by increasing the volume, you're actually now favoring the idea of gas expansion. And in order to fully expand and occupy the volume available to you, if you increase it, the equilibrium will shift to the side that has the most gases, because that will ensure that you will truly occupy the entirety of the volume that you have added onto what you had originally. So increasing volumes, shift to the side that has the most amount of gases. Decreasing volume, shift to the side that has the least amount of gases. But now let me present to you an interesting situation. Let's say that the gases you're dealing with are H2 plus I2 forming two HIs. Alright, in this case, the equilibrium expression, as we've already seen, is HI squared divided by H2 and I2. If you change that in terms of moles per liter or moles per volume, you're going to have mole square over volume square for HI. On the denominator, you'll have moles of H2 over volume of H2 times volume of I2 over volume of I2. And since the volumes are all the same, you end up with volume square on the denominator. And check this out. You have volume square on top, volume square on the bottom. The volumes cancel out, and you end up with just moles over moles. And here, it doesn't matter whether you increase the volume or decrease the volume. The volumes have canceled out, so the effect is going to be zero. You have no change in the equilibrium when the volume of gases, or excuse me, when the moles of gases is the same on both sides. We have 2 moles of gases on the reactant side. We have 2 moles of gases on the product side. So that's just something to be aware of. QC will basically equal KC in this case. We expect no change by changing volumes, when the amount of gases on the reactant side and the product side are the same. So to kind of summarize what we've seen with the volume, and using this delta N, which is basically the amount of gaseous products minus the amount of reactant gases. So in that case, if you end up with a positive value, this will tell you that you have more gaseous products. And if you have more gaseous products, increasing the volume will shift to the product side, will shift the equilibrium to the product side. Decreasing the volume will want you to shift to the reactant side because that will have the least amount of gases. However, if this value of delta N is negative, that means that you're going to have more reactants than you do have products, at least in the gas phase. And what that means is that if you increase the volume, you will now shift to the reactant side because that's where you will have more reactants. If you decrease the volume, you'll shift to the product side because that's where you will have the least amount of gases in this situation. And if it so happens you have the same amount of gases on both sides, then delta N will equal 0. And in that case, increasing or decreasing the volume will have no change whatsoever on the equilibrium. All right, the last one that we need to talk about is temperature. And for this one, I'm going to get to the point. In the PowerPoint, I actually show you uh, all of these graphs, the reaction coordination diagrams, and I kind of depict the fact that if you increase the temperature, you increase the rate at which you can make it over the activation hill. And that's all nice and good. Um, but I'm kind of gonna get to the point here. What happens is that as the reaction starts proceeding forward, and as you increase the temperature, you're gonna start forming more products. You're gonna form more products. You're gonna form more products, and at one point, you will have more products than reactants present in your solution. So increasing the temperature will have the same effect on the products as it did on the reactants to move the reaction, in this case, back to the reactant side. So what this means is that you want to have some temperature for sure to surmount the activation energy to go forward and lead to products. But if the temperature is too high, what's going to happen is that now the products will have enough energy to go back, and that will diminish the amount of products that you can actually produce. So in a reaction like this, where the reactants are at a higher energy than the products, meaning that you are dealing with an exothermic reaction, you don't want. There you go. Yeah, we're going to bypass that. You don't want to increase the temperature. And we're going to show you in a second with the equilibrium expression why that is. Now, in a reaction that's endothermic, where the products are a higher energy than the reactants, here you definitely want to increase the temperature as much as possible because you want to ensure that you have enough energy to surmount the forward activation energy. The second one, yeah, I mean, you have no choice. You're going to go back anyway, but you want to make sure you have enough energy for the reactants to make it in the first place to the product side. So here you will definitely want to increase the temperature. Now let me show you how this plays out when you do equilibrium. This is probably the more relevant portion. In the following equation, we have a bunch of gases, but I'm depicting an exothermic reaction, which means that you will have heat being produced. And as such, we can treat it as if it were a product. And if we treat the heat as if it were a gaseous or aqueous substance, then technically for an exothermic reaction, the heat will have to end up on the product side of the equilibrium expression. And so check this out. Increasing temperature, we're going to associate with increasing heat. Decreasing temperature will associate with decreasing heat. So if you increase the temperature of a reaction that's exothermic, what you will end up doing is increasing the amount of product that you have. And that will make your Q greater than your K. And because of that, this will favor the reactants. So this is kind of what I was trying to explain to you with the reaction coordinate diagram, that if you do increase the temperature in an exothermic reaction, you will basically sort of sabotage the amount of product that you could get otherwise. So you actually want to keep the temperature as cold as possible. And it's kind of interesting because I never thought about this, but when you do carry a reaction that's exothermic, we usually, chemists, put ice around it. And I thought it was mostly because you didn't want your reaction to become too hot to boil your solvent, or for bad things to happen. But in reality, what I was doing all along is placing ice on my reaction to decrease the temperature so that I could actually favor formation of the products. That's what I was doing all along. It took me years to realize that was the case. Now, decreasing the temperature, however, as I was telling you, will decrease the amount of product because heat in an exothermic reaction is in the product side. And so that will make your Q smaller than your K, and now you're going to favor products. So the exothermic reaction, you want to decrease the temperature to favor the products. In an endothermic reaction, however, the heat is being acquired, so the heat's actually on the reactant side. And so it will now appear on the denominator of your fraction. If you increase the temperature, you will end up increasing the denominator, which will make your Q smaller than your K, and this will favor going to the product side. If you decrease the temperature, you will decrease the denominator. In this case, the Q becomes larger than your K, so you you'll become reactant favor. And another way to look at this is that heat's on the reactant side. If you add heat, you're going to move to the opposite side. If you remove heat, you're going to move to the side where the removal is taking place. So if you treat it from the point of view of a simple reactant or product, you can base it just on the idea of addition or removal of product or reactant. And just keep in mind that increasing temperature is the same thing as increasing heat. Decreasing temperature is the same thing as decreasing heat. So now you know that, yes, for an endothermic reaction, you're going to have to put in heat to make more product. For an exothermic reaction, you're going to have to decrease the heat as much as possible to increase the amount of product. And the table right here summarizes that if delta H is positive, this is an endothermic reaction. The heat's going to be on the reactant side. Increasing the temperature will shift to the product side, the equilibrium, and decreasing the temperature will shift the equilibrium to the reactant side. In an exothermic reaction, the heat is a product. Shifting to the reactant side will imply that you have increased the temperature, and decreasing the temperature will shift the equilibrium to the product side. So with all that, this is the qualitative way in which you are to predict where the equilibrium is going to shift. Basically, I'm just going to tell you this is the equation, this is the balanced equation, this is the stress applied to the equation. Tell me what happens to the equilibrium. Does it shift to the reactant side, to the product side, or is there no change? And that will be the extent of what you need to do in regards to the Chatelier's principle. With all that being said, we are finished with equilibrium. So I hope you enjoyed this lecture series, and I'll see you on the next.